Hi everybody. I wanted to just do a very quick video to talk about the statement that you see on the screen. And the statement is that Kepler's second law, that's the law of equal areas in equal times, that law is really a consequence of angular momentum conservation. Okay? And I'm going to also, in the process of this, show you a very helpful mathematical connection. Okay, and I'm going to write that down here. But Kepler's second law states that planets will sweep out equal areas in equal times. Okay, and that's really basically saying that if you look at the rate at which the area is changing, that rate should just be a constant. I'm not going to redraw that picture, but, well, maybe I should, where you've got planet here, and you've got some type of orbiting object over here, and the idea would be that in a certain amount of time, that object moves from here to here, right, in a certain time. But if you look at the object at any other place on the ellipse, that it will sweep out an equal area in the same amount of time. And so the areas that we're talking about are those two areas. So those are the same, right? So this area and this area are the same. That's the law of equal areas in equal times. Okay. So from a math point of view, you could say that the rate at which the area is changing is a constant. That's what this mathematical statement means. If you put a derivative on it, it just means the rate of change isn't changing, right? It's a solid number. So that's an important thing, right? I will show you, hopefully in just a few minutes, that constant is related to the angular momentum of the object that's orbiting. Okay, so there's actually a thing where it's that rate of change is equal to the angular momentum divided by 2 times the mass of the object that's doing the orbiting. So that's this m, right? Not the mass of the sun or whatever. So that's what I wanted to show you. This is a very, very useful relationship. Okay, so I'm giving you the answer first. That this is a nice thing. This can help you with some problems if you know this relationship. Now, what I'll show you next is just how do you get to it. I don't want you to feel like you need to know all this in detail, but I'm just going to show you real quick. So watch it and see if you can get the idea of this. Let's talk about having this. I'm going to draw the mass here. So this is m. And it's going to be moving along some type of a path. At a certain radius. Okay. So, hey, why don't we call that the Earth? The mass is the Earth, and we'll call this the Sun. Now, I don't know if that's the best thing to do here, but I mean, the Earth makes a very circular orbit around the Sun, but we can still use that as our example. So here's the idea. What I want to do is come up with a way to talk about the area of this sector. Can I write an expression for the area of that sector that's based on the fact that this distance is r? And then we're going to make this angle inside of here a d theta, so it's a very small change in the angle. Okay. And the answer is yeah, you can do that. Okay. So if you think about it, this is very much like a triangle, isn't it? With the area that's shaded in. And if my d theta is really small, that's very much just like an isosceles triangle, where 2 of the sides have a length r, and then that third side is something that's really short. So you can basically say for that triangle that the area inside of it is going to be 1/2 times base times height. Yeah, that's right, from geometry, right? So the area of that is 1/2 base times height. And what we do here is we'll say, well, the height of that triangle is going to be awfully close to the radius. So I'll put that in first, right? Because the height would be like this part of the triangle, and that's really, really, really close to the radius, especially if you make this d theta really, really small, like calculus small. So we can do that substitution. Now, the base is this part, right? The base comes from math. Remember when you learn about radians and arc lengths and things like that? Well, if you've got an angle here and a radius here, that distance between those points, that arc length, is radius times d theta. And again, we're talking about really small d thetas, like calculus small. And so we can make that approximation here. I know it's a curve. I know this is actually a curve. But if you make d theta really small, it's kind of a straight line. Okay? So this is what we get. You get that relationship. Okay? Now, we'll combine that with a different way of looking at this. And here's the different way of looking at it. If you've got the mass, again, from here to here, moving on that path, right, with those radiuses, then you can also think about this as that mass having some type of a velocity here, which is perpendicular to the radius, okay? And so that's moving along. And that velocity is kind of like its tangential velocity, okay? And so that perpendicular velocity is going to be equal to the distance right here, the r d theta we talked about before, right? That really short distance of arc length divided by the time it takes to move from one point to the other. So this is just like a different geometrical way of talking about, hey, what is the velocity of those 2 points? So again, the first picture I didn't talk about velocity. I just talked about a change in angular position in a little arc length. In the second picture, I'm talking more about the velocity. Okay? So I'm going to take that. And the reason I did that is because I can now take my r d theta and I can actually just do a substitution because I see there's an r d theta that's over here as well. So that's what I'm going to do, and then that's going to lead me to the momentum statement that I gave you at the beginning. Okay? So I'm going to take this part here and I'm going to plug it in for r d theta. So I'll just keep working down here. So this is 1/2 times the perpendicular dt times r. And you know why I'm doing this, and if I didn't make this clear before, is because now I have dA and I have dt. And you know what I'm going to do next is I'm going to bring the dt over, and then I'm getting really close to the expression that I started with on the last page. So you got dA over dt equals 1/2 r times that perpendicular velocity. Okay? And so now you say, well, how does that equal like angular momentum divided by 2 times mass? Well, it does. So what you have to remember is I can't spell remember. You have to remember how to spell remember that L is equal to R times M times V perp. That's something I hope you remember from last week when you learned about angular momentum. And so what you can do is basically kind of kick out this stuff, okay, because it's there. And so let me show you. So you've got R times V perp is equal to L over M. So I can take this, put it in, and I'd be left with 1/2 times L over M, which is what I wanted to show you in the beginning. Okay. So again, what are we trying to show? We're trying to show that the rate of change of area is a constant, and we're showing that how it relates to the angular momentum of that object which is orbiting. Okay. And so that's the idea with that. Okay? So, you can look at this different ways. If you were an early astronomer or physicist and you were observing from your data, you were observing that the planets were sweeping out equal areas in equal times. If you would observe that, that's actually a way of proving that angular momentum is conserved, or at least showing it. You're not proving it. But if your areas are always sweeping out the same areas for every same amount of time, it's showing you that L over 2m is constant. Okay? And that's a way of showing that angular momentum is conserved for orbits. Of course it is, because we know that in order for angular momentum to change, you have to have an outside torque acting on the planet, and that just doesn't happen, right? I mean, unless you've got some nearby star or something which is acting on it. So the fact that it works out this way is kind of supporting the idea that the angular momentum of your object is constant as it orbits around. Okay? All right, so I'm going to keep that short, but this is the takeaway. This is just kind of giving you the backstory on where that comes from. This is an important result, so put that in your pockets. All right?